Welcome back. So our last one to look at today is we're going to have an exploratory analysis of some trigger point data. So this is some exploratory data analysis on counting on an experiment where we counted the number of myofascial trigger points, which are basically sort of little knots in the muscles that cause pain. And it was specifically in racing greyhounds in the Manawatu. The idea of the study was to see whether, first of all, whether having trigger points led to reduced performance in greyhounds, and whether treating the myofascial trigger points to try and get rid of them during the study would cause some greyhounds to improve their perhaps their flexibility and thus their racing speed. And so what we did is we got a bunch of racing greyhounds from the greyhound people in the Manawatu, and we randomised them into two groups, and then we measured them at baseline. So before we started treating them, we essentially counted the number of trigger points that the vet could find, essentially by palpating muscle and looking to see where the greyhounds had sort of knots in their muscles that caused them pain. So this is all pre-treatment, so we hadn't treated them. So after this, we then went on and actually treated one of the groups and did not treat the other group. So we had a control group and a treatment group, and then we could see sort of how things changed over time. But we're looking at the data just at baseline, so before treatment. So here's what the data looked like. So it has essentially 5 variables: name, sex, num, pain, and treatment. And we can read the data in using this command here, which we will run. Okay, and you can see that when I ran that, I didn't get any output, but I did get a new data variable here called TPS, which is the name I made up down here. If I click on that, I can see my data. So here's my 38 racing greyhounds. There are their names. Some of them I'm using, some of them not. The sex of the greyhound, and this is the number of trigger points that was found by the vet on inspection of those greyhounds. There's a pain score, so each of the trigger points were evaluated or given a pain score from 0 to 5 based on the sort of the reaction of the greyhound when that trigger point was palpated. And then, so this is the sum of the pain scores across each of the across all of the trigger points on the dog. So you can see that these tend to correlate, right? Higher number gives higher pain. And then this last variable is 1 if they're in the treatment group and 0 if they're not. So that's in the control group. And so because this is all at baseline and because we randomize the dogs, what we would expect is that these groups be somewhat similar, okay? In terms of the number of trigger points, in terms of the sex, that should be relatively similar, and in terms of the pain score, they should be relatively similar, right? Because all we've done is randomize the dogs into, using a random number generator, essentially tossing a coin to determine which dogs were in which group, and then we measured them, right? So we're going to have a look and see what randomness gives us, okay? And in this case, it didn't give us, it gave us things that we perhaps don't really want, but nonetheless, this is what randomness gives. Okay. Right, so we've had a look through the data. Now we're going to add a new chunk below using the summary, and then use the summary command to summarize this data. So 2 ways to do that. I could go insert and then R, and it gives me that outline, the delimiters that I need to give me my code block. The other way I could do it is I could just copy and paste another one, right? So I could just copy that one and put that in there and then change it. Right, just delete the code that's in there and write new code. So we're going to do summary. We did that before, didn't we? So summary of TPS. And so again, we get this data, we get this output here. And you'll notice that, again, things are slightly different. Okay, so we notice that the name and sex variables have been interpreted as being character strings. So these are just labels. The num and pain variables have been interpreted as numeric, which they should be. That's fine. But the treatment column, which is zeros and ones, has also been treated as numeric. And the treatment column, of course, is actually just, is specifying which groups they're in, right? So, it's just a bunch of ones, which mean it's in the treatment group, and a bunch of zeros, which means it's not, right? So we can compare this to the sex variable, which is, a bunch of labels. And notice that when I did the dollar there, in order to pull out a column, so the dollar is short for pulling out a column, it brought up a handy little sort of pop-up that I could use to select the variable that I want, which sort of helps reduce typos. Okay, so the treatment is a bunch of numbers and has been interpreted as a bunch of numbers. The sex is a bunch of labels and has been interpreted as a bunch of labels. Okay, so one of the things that we'll need to do later is we'll need to convert the treatment variable to a grouping variable. Okay, we'll do that later on. Okay, so referencing a single column from a data set, you can use the dollar to pull it out. Okay, so for example, we could also pull out the number of trigger points in the same way. Okay, so once we've got a single column of data, then we can do summaries of it by, for example, tabulating it. So a better summary than this one for the treatment, because it's a bit silly that, computing the mean on which treatment it is doesn't really make any sense. All it means is that, the mean at 0.5 means that half of them are 0 and half of them are 1, doesn't it? Instead, we might want to table up the treatment, which the table command can be used for. We could table up the sex as well, I suppose. So how many do we have? So we have slightly more males than females in the data set. Same number of dogs in the treatment group and the control group. Okay, so that's a better way to summarize it, but later on, in order to use this for graphing and summarizing things sort of automatically, it would be nice to be able to tell RStudio that even though the treatment variable is a bunch of numbers, we want it to treat it as if it's groups. And we can do that with the factor command down here. So let's break down what this one is doing. The factor command is taking the treatment column, all those zeros and ones, and converting it to a grouping variable. So essentially what R is going to do is it's going to go through and go, well, how many zeros do I have, how many ones do I have, how many other things do I have, and just sort of add a tag to that variable such that it knows that these aren't really numbers, they're actually labels. But then we've gone and assigned that into a new column. So TPS $group would be the group column in the TPS data. But of course we haven't created that before, we're just creating that on the fly here. Okay, so when I run this command, notice up here I've got TPS currently is 38 observations on 5 variables. When I run this command, it's 38 observations on 6 variables. And when I have a look at TPS, I've got that extra variable group, which looks the same as treatment, but you'll notice that it aligns it. The alignment is different, right? So this is right aligned, the treatment column, whereas the group column is left aligned. And of course, the right aligned things are numbers, the left aligned things are grouping variables. So you can sort of tell just by looking at it that R is treating these things differently. And now, of course, if we do a summary on the TPS data, the group variable has been summarized in the way that we would assume it should be, given that it is a grouping variable. It's been tabulated. Okay. Notice that the sex variable hasn't, even though perhaps it should be. We could do the same thing here. So, for example, we could use sex group, right? And we could convert that to a factor in the same way. And now, when we summarize it, the sex group variable has been summarized in the way that we would expect. Now it turns out that R is going to treat the sex group and the sex variable when we go to do plots and tables and things in exactly the same way, even though they look differently in the summary. Okay, so when it sees a character vector or a labeling column, it'll essentially convert it to a factor variable on the fly for us. But nonetheless, converting it ourselves just sort of make sure that things are around the right way. The other thing that the factor variable can do is it can specify order. So by default, factors will be ordered alphabetically, so you can see that females come first. Here, if we wanted males to be first, then when we set up the factor command, we could have reordered it. We'll see that in a later computing lab. Okay, so now we might want to do some plotting. So here we are, we're going to do a histogram of the number of trigger points. Right, so here we're summarizing a numeric variable. So let's have a look at the data. Here's our numeric variable here, which is the number of trigger points. And whenever you summarize a numeric variable, then essentially what you're looking at is you're wanting to look at the distribution of those values. Right, so you could summarize it using a point estimate, like just compute the mean or something. But often it's the distribution that is useful to you, which of course is what a histogram will give us. So here's a histogram. So what we've done here is we've divided up the scale, the range that the number of trigger points varies over, which goes from 0 up to just over 30. We've divided it into little sections, and for each section we've counted up the number of dogs we have with that number of trigger points. So there's one dog that has about 30 or a few more than 30 perhaps trigger points. There's 2 dogs that have between 25 and 30 trigger points. There's 3 dogs that have between 20 and 25 and so on, right? There's 3 dogs that have a very low number of trigger points. The most common number of trigger points is about, sort of 12 to 15, this bar here, where there's, I guess, 11 dogs in that category there. So we can see here that most of the dogs have sort of fewer than about 20 odd, but some of them are quite high. So we can see we can kind of get from the histogram a measure of center and a measure of spread and potentially a measure of shape. Okay, there's slightly more sort of at the lower end than there is at the higher end. Now, when we created this histogram, we specified the number of bins, which is the number of bars that is used for the histogram. And a small number of bars is going to give you a very coarse representation of the data. Right? So shape is hard to see when we only have a few bars. I mean, the obvious silly one is if there's only one bin, then, all you're saying is that I've got, 38 dogs and that they've got somewhere between 0 and 32 trigger points. That's a bit silly. If I've got two bins, I get some small representation of shape. And it's only when I go much larger than that I start getting detail. But I can go too far, right? So here's 30 bins. Then when I have 30 bins, so I've divided the range of the number of trigger points up into 30 different categories, then a lot of the categories have 0 dogs in them, and the other categories mostly have sort of 1 dog in them, or 2, And so it's hard to get a representation of shape because you just have all of this noise in here. So somewhere between a high number of bins, super noisy, hard to see the signal, and a low number of bins, no signal at all, is sort of some optimum. Okay, so maybe it's sort of 10 or 9, essentially what should be happening is that as I change the number of bins, it shouldn't change my view of the shape all that much. Now, in this case, we've only got 38 observations, so it's going to shift quite a bit based on the number of bins, just because of how they'll fall, how the individual, where the edges of the bins are and how they fall left and right around that. But you can see that, I tend to get the same result, which is that the most popular value is sort of about 12, and there's more dogs with fewer than 12 than there are with more than 12. Okay, so I describe this as centered at about 10 to 12 trigger points per dog. Range goes from 0 to 30 odd trigger points on a dog, and more tend to be lower than 12 trigger points then higher than 12. Maybe a little bit skewed to the right. Only 38 dogs, so we don't have a good measure of shape here. Okay. Now, of course, this is all dogs, and really what we wanted to know perhaps at the start is, do our two groups that we've put the dogs into, so our grouping variable treatment here, are these two groups actually similar before we start the trial? So we'd expect them to be, because we randomize them, right? So we would expect the groups to be the same because we've used no information to put them in the group other than complete randomness. So ideally, the two groups should be the same in terms of the outcome measure, which is the number of trigger points. And we could start looking at that by simply changing the color of the bars based on the group that we have. Okay, so here we'll get the same plot as we had up here, but the interior, the fill color of the bars has been shaded based on the grouping variable. Okay, so here is all the treatment dogs down here, and these ones up here are the control dogs. And we can immediately see from here that the treatment dogs all have fewer than about 16 trigger points, whereas the control dogs, some of them have fewer than, have a small number of trigger points, but about half of them probably have more than 16 trigger points. Okay, so that the treatment group, which is group 1, have fewer than 16 . The control group, group 0, has more, has some dogs, about half of them, with more than 16 trigger points. It seems the groups differ. Nonetheless, this is a little bit hard to compare because in terms of the shape of the distributions, because the red distribution is starting on top of the blue one, right? So its shape is distorted by the shape of the blue one, right? So we can correct for that with by basically just offsetting the red bars from the blue bars, so that everything starts at the baseline. So we can use position equals dodge for that. Okay, and then we get this here. So all that's happened is that we've sort of shrunk up each of the bars so that we can display them next to each other. Again, we see that the treatment group, the blue bars, are all sort of below 15 or 16, whereas the red bars, a bunch of them are actually higher than that. Okay. So it appears that the control dogs tend to have more trigger points than the treatment dogs. This is strange because the allocation to group should have been completely random. So just by chance, okay, that's important, just by chance, because it was random, we ended up with two groups that are quite different. This might be a little bit of a problem for later analysis, for the trial basically, right? As two groups start from different levels. Nonetheless, the only reason for this is random. Okay, and so this is an important point really, in terms of statistics, is that things that seem quite strange, like one group being quite different to another group, happen just due to chance fairly often. Okay, so this was purely random. The vet that was counting the number of trigger points did not know which group each of the dogs were in, but nonetheless, we found that the control group of dogs tended to have higher number of trigger points than the treatment group. So this is going to be a problem for the study in terms of the treatment groups start with fewer trigger points, and so reduction in the number of trigger points will reduce them even further, and maybe there's not even that much scope to reduce them further perhaps. Whereas perhaps there's scope for the control dog's number of trigger points to drop off naturally, and so it's going to be potentially hard to distinguish those two things, right? Because the two groups are different in terms of the outcome variable of interest, just by chance, not due to anything sort of inherent in the allocation or anything. It's just purely luck that this happened. Nonetheless, due to that difference at the start, it might be that it's hard for the experiment to be able to extract information about the effectiveness of the treatment later on. Okay, so we could try altering the scales and fixing up the axis label, so this is a bit better. Let's grab that code block and copy it down here. Okay, so for example, we could add some labels. So what could we add? Well, we could change the X label to number of trigger points. We could add a title, maybe so maybe that'll be the subtitle. Title might be distribution of trigger points at the start of the study. Okay. The count variable there, y, could be number of dogs. Right, there we go. Number of trigger points, and then number of dogs having that number of trigger points. We could change the group here. We could put, so that's the fill, isn't it? The fill aesthetic. So when we change these things here, the X is corresponding to this here. The Y is generated by the histogram. So if we wanted to change the label for group here, we would change the fill label because that corresponds to group. Right, fill is there, fill is there. So the things that you put in labs should match up with the things that you put inside the mapping. So the fill is going to be the treatment group. Okay. And we might want to change the colors. So how did we change colors? Let's look up here, back to where we did that before. Okay, here we use the scale color manual. So let's copy and paste that. I'm going to put that here. So we need a plus at the end of the previous thing because we're adding some more stuff on. And then we need our scale color manual. And we'll only need two colors, won't we? Let's do dark green and orange just so that we can see it working. Okay, so we'll run that. And that didn't work. Right, so that's because, of course, I haven't specified color in here in my mapping. So because I haven't specified the color in my mapping, it's changed the colors, but we haven't used color. Instead, we've used fill. So there's two colors when you're drawing a bar. There's the outside of the bars, and there's the inside of the bars. So the outside of the bars is color, and the inside of the bar is the fill. So if I change the aesthetic that we're using to color to demonstrate, you can see that it changes the outside of the bar. The inside of the bar is all the same color. The outside of the bar changes depending on which group you're in. So you can see we've got orange and green because we've updated them with scale color manual. So because we use fill instead, because that gives us a better picture, we're going to change our scale color manual to scale fill manual. So essentially what happens is that every aesthetic that you have on the plot, so here we have the X aesthetic and the fill aesthetic, each of them has a corresponding scale, right? So the X has the scale along the axis here. We could change that with scale X, manual, for example. Similarly, the fill, the color that we use to fill the bars, has a scale, and we can change it with scale fill manual. Now we've specified the values are dark green and orange, but we could also specify the labels if we want as well. So we could say control and treatment for the labels, and that will override the whatever values are specified in the actual data set with what we want them to be. Okay, so we've got the control group and the treatment group. I guess maybe we probably don't need treatment there twice, do we? Maybe we could do it like that. Okay, so there's a tidy sort of form of that graph. Now the last thing we're going to do is we're going to knit this document, and that's basically press this button here, and what that's going to do is it's going to combine all of the writing that we've done here and the code and the output, essentially what we see here, but it's going to format it a little bit nicer and produce an HTML file ready to go on the web. So we'll click that button. What it does is it's doing a bunch of stuff down in the console here, and it gives me this much nicer to read HTML document that has all of the writing up here, all of the code that we've done, and the output from that code in line. So if we go further down, we'll get some graphs. There's a graph there, okay, with all the writing that we have about it and so on. Okay, so down here we'll have our trigger points. Here's our graphs, and there's the last one that we did down there. Okay, I'll upload this now to stream.